All right. So we're happy to have our next colloquium speaker, and that's Anasuya Acharya. So Anasuya was a master's student here. She did her MTP here, MTech here, and then currently she's doing a PhD with Professor Karmit Haze at Bar-Ilan University. And she'll be talking about some of her recent work during her PhD. So without further ado, Anasuya can get started.
Okay. Hello, I'm Anasuya, and today I'll be talking about scales. This is a joint work with my PhD advisor, Karmit, and also Manoj and Vlad. And yeah, so I've been told that this is a talk for a very general audience, so I tried being as well first principle as possible. So here is the outline of my talk. We'll just start with what secure multi-party computation is, and then move to the YOSO model, which is the motivation towards us designing the scales model, and then we'll look at how to make a protocol in the scales model, and for that we need the main building block that we need is garbled circuits. We'll talk about that, and rerandomizable garbling, and then we'll talk about the protocol. So to start off, what is secure multi-party computation? This is, so the problem statement here is, it involves n different parties, say P1 to Pn. They're just entities, and each of them have their own inputs. So P1 has an input x1, so on and so forth. Pn has xn. Now, they want to compute a function f on these inputs, and well, in an ideal setting, what would be convenient to have is this one big box that is trusted and to which each party can give its inputs, and the box can then compute the function output and give it back to all the parties. And so each party knows only its input and the function output and nothing more. But, well, what we do in MPC is try to have the same effect without the box. So now each party exists, they have their own inputs, and they communicate with each other in an all-to-all way, typically. And at the end, and this communication is according to some protocol, and at the end, they end up with f of x, the output. And so the security guarantee that we typically want is that everything, all the messages that they see within the protocol does not reveal anything more than their input and the function output. So that's basically MPC. So that's cute and all. So what can we, let's look at an example of something that we can do with MPC. So one such thing is a functionality called Oblivious Transfer. So this is a problem with a sender and a receiver, and the sender has two strings, S0 and S1. The receiver has a choice bit B, and in the end, the receiver needs to get one of these two of the sender strings that it chooses according to B. So it gets SP. So the protocol needs to go such that the receiver does not know what the other string of the sender is, and the sender does not know what the bit the receiver used is. So now how would we create such a protocol? So here we have the sender and the receiver again and their inputs. So for the first message, say the receiver, it generates a public key and a secret key for any particular encryption scheme, and this corresponds to the receiver's choice bit, and and it also creates another extra public key. Now what it does is it sends the two public keys to the sender in the order 0, 1, whatever, and now the sender, and this is the receiver's first message. the sender will now take PK0, the 0th public key, and encrypt the 0th string with it to get a ciphertext C0, and the same with for S1. And now the sender creates two ciphertexts, and these is what is sent to the receiver back. And the receiver only has the key the secret key corresponding to its choice bit. So it can decrypt only one of these two messages. And well, and that's why the protocol works. It is secure because the receiver can't know the sender's other message, and the sender does not know, well, the receiver's bit. So this is Oblivious Transfer. This is a two-message protocol, and that's that. Now, what we are interested in is to compute general functionalities, like any functionality at all, and among a lot of parties. Say, instead of having two parties, we have like millions of parties, and they all have inputs, and there needs to be a computation that happens among all these parties so that everybody ends up with the output. Now, the problem with scaling MPC to such a large set of parties is typically that you can no longer say that now everybody needs to talk with everybody, because communication blows up. Now, so, and also you can't think of, say, only one party misbehaving anymore. So we normally think of it now as, say, we have an adversary that controls a group of the parties, or it can see whatever this group of the parties sees. And so, and well, yeah. And so we would typically want this adversary to not control enough of the parties so that it can, so that the protocol still remains secure. And one way this is enabled is using this model called YOSO, you only speak once. So what happens here is that you have like a whole big pool of parties. Now, there's an adversary that corrupts a minority of these parties. It can't corrupt more than half of the parties. And we can't have all-to-all communication because that's inefficient. So typically what happens is that only a set of a committee within this pool is elected. Everybody shares their input among the members of this committee. They do some computation, yeah, and then they post a message. And while they post the message, so once they're done with the computation, they erase their internal state, all the randomness that they used, and then they post this message. And then what happens is that this committee, which is typically smaller than the entire server pool, is if it was known, then the adversary could come and corrupt all the members of the committee. But the committee only reveals itself when it's posting a message. So, and at this point, it has already erased its state. So the adversary can't gain anything by corrupting these parties. So now, so once this committee has spoken once, it's basically gone. And now the next committee comes up, picks up the messages and continues the computation, and so on and so forth. So this process of, say, one committee coming up, doing some local computation silently, then erasing its state, posting a message, and then basically dying. A protocol that takes this form is, well, a protocol in the YOSO model. And why it's neat is because the adversary does not know who to corrupt until it's too late. So, yeah. Now, that's great and all, but the existing YOSO protocols are, well, they're expensive. So one reason why they're expensive is because they use something called target anonymous channels. So what target anonymous channels is basically a mechanism that tells, okay, so that selects the next committee. So in a sense, what's happening is the previous committee, they post a message to everybody, but then this message is created and encrypted using the next committee's public keys without knowing who the people in the next committee are. And the person giving these public keys and figuring out who this next committee is, all this happens as this setup in the cloud that, well, that the adversary shouldn't be able to completely know or corrupt. So, and this setup is kind of expensive. So there is that. Also, computation happens in rounds, and each round needs an n-party committee. N needs to be large enough so that there is an honest majority within each committee, and the number of rounds is proportional to the size of the computation. Say, if I need to compute a circuit of depth d, I need d rounds. So, yeah. So, how can we make this better for us? So, for that, we introduce something called the scales model.
So, Anasuya, we have a question here.
Okay.
Go ahead.
Yeah, actually, I wanted to.
Oh, okay, go ahead. Yeah.
Actually, I wanted to know how the small groups which were being used in the YOSO model are selected. I mean, how every time new set of the nodes are being selected as the generators of the operators, how they are selected? Is there any particular algorithm that runs behind that, or?
Yes, so that exactly is what target anonymous channels are. So one way of doing that is basically saying, okay, now there is an electing committee that self-elects, in the sense that I do something, say like a proof of work, and then I know that, and then I gain a certificate. If I win the proof of work, I gain a certificate with which I can say that, okay, now I can select one person in the next computation committee. And like that. So a bunch of people gain such certificates, and then they select one person each in the next committee. So, and once you select, you select the party in the next committee, you take that party's public key, you randomize the public key and create another public key for its secret key, and you post that. So people in the previous committee will pick up the randomized public key, encrypt the message using that, and leave the message out in the system. Now, when the previous committee dies, everybody tries to decrypt that message, and the person who successfully decrypts it, because their secret key corresponded to the public key, is part of the next committee, and they start doing their computation. That's basically typically how it works.
Okay, so what if an adversary tries to elect, let's say he has distributed his persons and tries to elect in multiple selections also, like the number of people, the adversary is not concentrated to one particular election committee, but he has distributed his members to different election committees also. In that case, he can try to.
Yes, exactly. So what happens is that if you're you get elected as part of an election committee by something like proof of work. So you need to solve a puzzle and you get elected. And the assumption that target anonymous channels works under is that say there is a 2/3 honest majority in the election committee, so that because we know that if an adversarial party gets elected, it's going to. Where I cut off last time, did you hear the answer to the question, or was that not there?
So we had a discussion while you were cut off. Yeah. So basically, that's kind of this outside of this particular work, right? There are many ways it can be done. So yeah, we're on.
Right. So okay. So well, bottom line, YOSO is expensive in many ways, and we in scales, the purpose is to maintain this speak once property for a certain set of parties. but to relax it for others, and then, well, to get better guarantees from that, from the whole setup as a whole. So moving on to the scales model. So in the scales model, we separate a server pool, and in the server pool, there are honest servers and dishonest servers. And unlike in scales, we also support dishonest majority. So over 2/3 or maybe 4/5 or something of the servers can be corrupted. So there is that. And then we have separately, we have clients, and the clients are the ones with the inputs. So servers only participate in computation and clients provide inputs. So there is that. And to streamline communication a little bit, we have a bulletin board.
By the way.
Yeah, I've started recording.
Okay. All right. So Anasuya, sorry for the interruption.
Okay.
Start again.
So, right. So there are servers and there are clients and there is a bulletin board. And so how a protocol in scales works is that it follows a particular communication pattern. So the clients, so first all the clients concurrently post one message each, and that's the first time the clients speak. Then for multiple rounds, and the number of rounds is a constant number. It has nothing to do with the size of the computation. In each round, one server comes up and posts a message. It reads the state of the bulletin board, does some computation, and posts a message, and so on and so forth. So one server in each round for a constant number of rounds. And then at the end, once all the servers are done doing what they need to do, or rather a small number of them, then the clients read part of the state and do some computation and post a last message. And this is basically it. So the clients speak twice. The servers are completely stateless. They speak once each, and we have a protocol in this setting that does not require target anonymous channels, in the sense that any one server can come up and continue the computation. It does not have to, so messages don't have to be encrypted to the next server in any sense. So that's that. So, and in the end, anybody can come read the state of the bulletin board and find the output. So what we support for now is semi-honest security, and the servers can be YOSO style adaptive corrupted, and they speak once, and all but one of the computing servers can be corrupted. And in the client, the clients speak twice. So we support static corruption for a certain subset of clients. And then after that, between the first and the second message, it can be corrupted. I mean, a bunch of other clients can be corrupted, so adaptively. And we are secure in that setting. So, and yeah. So apart from that, there are certain, neat features that a scales protocol has, and we only need one, and one of them is, and a few of them is here. We only need one on a server out of all the computing servers. We need a constant number of servers and one message per server, just as in YOSO. And we don't need target anonymous channels, just as I said. And clients can, in a sense, with their second message, control when they want to be done with the computation. So all the servers basically do a symmetric kind of work, and once the clients think that enough servers have computed, then such that one of them would be honest, they can stop the computation. And scales is an abbreviation for small clients and large ephemeral servers. So clients do work only proportional to their input size and the number of servers. And the servers are the ones who do work proportional to the size of the function. So that's scales. Now, how you create, in order to create a scales protocol, we use something called rerandomizable garbling. So before going to rerandomizable garbling, let's first look at what garbled circuits are. So yeah, don't be intimidated. This is not that, well, yeah, it's not as complicated as it looks. So garbling is basically the process of taking a function that you want to compute and creating a representation of that function called a garbling or a garbled circuit. And so this is a special representation, and and why it's special, we'll get to that in a minute. So the garbling algorithm also creates labels for each input. And so if a function takes, say, m bits of inputs, for each bit, 2 labels are created representing 0 and 1. And so this entire set of labels is something we denote as this E over here. Now, depending on what the actual input is, you basically pick out the labels that correspond only to this input. So if the first bit position had labels for 0 and 1, you pick out the label for x1, the bit x1, and so on and so forth for all the input bits, and that becomes this capital X over here. So capital X is special in the sense that it has a set of labels, and the labels do not reveal what the input is at all. And now, given this set capital X and this garbling F, there is a special procedure that allows you to evaluate the garbling on these labels, and in such a way that it reveals only the function output and nothing more. So that's basically what garbling is. So it's a magical function that algorithm that represents a function in a special way and inputs as labels, such that another evaluation function can take this garbling and labels and get only the output out of it. Now, how do you garble? So the first step to garbling is you take a function and you convert that into a circuit representation. And yeah, so in the circuit, say each wire is labeled, say W1 to W5 for this example, and each gate is also labeled. And now what happens is, so each gate has a gate functionality. Let's take G1 for example. So G1 has 2 input wires, W1 and W2, and an output wire, W4. And this is the AND functionality, for instance. Now how you garble is basically for each wire, you sample 2 labels to represent the wire. So you have a 0 label for the 0 value and the 1 label for the 1 value. And now you say effectively in the truth table, you replace the 0 value with the 0 label and the 1 value with the 1 label. And there's that. Now what you do is you take for the output wire W4, you take its 2 labels and you share these values. So sharing is basically taking, so for the label L04, which is a string, what you do is you sample 2 different strings such that their XOR is L40. So that's what sharing is. So each share on its own does not reveal any information about the actual string, but when you put these shares together, you XOR them, you get the string. So so you take the output label, both the output labels, and you share them. And then what you do is you encrypt the share with the input label as the key. So So for each row of the truth table, you will see that there are 2 ciphertexts over here. And this set of 8 ciphertexts is a garbled gate. And you can do this for every gate in the circuit. Now, note that if I have only one label for each wire, for each input wire, say I only have L01 and L02, then I can decrypt only one row of this truth table, which is, say, the first row. And the rest of the rows still remain as ciphertexts, and I gain no information about it. So to evaluate a garbled circuit, you get one label for each input wire, and you decrypt one row of the ciphertext to get, and you reconstruct the share to get one label for the output wire, and so on and so forth. That's how you evaluate a garbled circuit. Now, garbling is neat because we can use it for multi-party computation. So for example, typically in 2-party computation, you can compute any general functionality, F, using garbled circuits. So in such a setting, what you do is you designate one party as the garbler and one party as the evaluator. Say G has input X and E has input Y. And for now, let's just say that these are 1 bit each. So now what the garbler does is it garbles the circuit and creates the garbled circuit capital F and the encoding, and it sends the garbled circuit to the evaluator. Now, the encoding has 2 labels for the garbler and 2 labels for the evaluator. The garbler knows its input, so it can send the label corresponding to its input to the evaluator as it is. Now, but now what happens is the garbler has 2 labels for the evaluator's input, and the evaluator has to pick one. And how it does it, we've seen this before, it uses OT. So the evaluator uses its input as the choice bit, the garbler uses the labels as the 2 strings, and OT gives the evaluator the label that corresponds to its input only, without the other label. Now, in the end, the evaluator ends up with the labels corresponding exactly to the input of the function, and this does not reveal the inputs themselves. And and then it can evaluate the garbled circuit on these input labels to get the output. So this is how garbled circuits is typically used in 2-party computation. Now, what we care about is we need to extend this to the multi-party case. So, and in the multi-party case, immediately, what you can see is that we can't do with just one garbler, because say one party is the evaluator, one party is the garbler. If the other parties do nothing, then what happens is that when an adversary corrupts both the garbler and the evaluator, it can see exactly what all the inputs are, because the garbler has all the randomness that was used to garble, and the evaluator sees everything that it gets out of the things that was used to garble. So this already doesn't work. So what we typically need is re-randomizable garbled circuits in which all the parties are involved in garbling.
So can you hear me? You cut off for a little bit, the very last part of the previous slide.
Okay, so I was just saying that in the multi-party case, you can't do with just one garbler and one evaluator, because the garbler and the evaluator, an adversary can corrupt both the garbler and the evaluator, and they can find the inputs of all the parties that are not involved in the garbling. So the solution to that problem is to have as many parties as possible garbling. So, and now, and we need to do that and recall our setting in which we everybody who does work proportional to the function size is a server, and the servers can only speak once. So we need to basically garble in sequence. So that's what re-randomizable garbling schemes are. So in re-randomizable garbling, what happens is that you have the first party that takes in a function and creates a garbled circuit, capital F. Then another party can take in a garbled circuit and add its own randomness to it and create another garbling, F prime, of the same function. So, and so on and so forth. So there can be one garbler, and every successive party after that can re-randomize the garbled circuit. So finally, what can happen is the last garbled circuit would have the randomness of everybody who participated in the garbling. And if even one person is honest among all of them, that one garbler's or re-randomizer's randomness is hidden from the adversary. And this basically makes it such that if an adversary corrupts both the garbler and the evaluator, and then it has no idea, so it can't say the difference between a re-randomized garbling and a fresh garbling of the function f, and that is what we need. So that's basically a top half of the picture over here. The bottom half is basically saying that I can garble a function and get a garbled circuit, and when I'm re-randomizing it, what needs to happen is I need labels that correspond to the re-randomized garbled circuit. Otherwise, I can't evaluate. So that's what this green circle here is doing. So this combines the projection to get a new input encoding. Now, so re-randomizable garbling is not exactly something new. People have done it before, but in our work in Scales, we are the first who, formalize it as well a notion and define it. So there have been constructions before, and we use a construction that already existed. So that's the construction in GHV10. So having seen that, so yeah. So how do we re-randomize the garbled circuit? We already saw that in a circuit, each wire has labels, has two labels, and out of them, input labels are kind of special. So input wire labels are kind of special. So now, and so when we garble the circuit, what happens is for a gate functionality G, you create, you basically garble the truth table of the gate functionality. And now to re-randomize, what we do is we basically use homomorphic encryption. You have a ciphertext that the re-randomizer gets. It has to do something to the ciphertext to get another ciphertext that looks fresh. So, and in a meaningful way, so you need homomorphism. So yes, homomorphism is heavy, but we don't use fully homomorphic encryption, which is, well, really heavy. So yeah. And how you re-randomize is basically for each wire, you pick a function. So for the wire A, you have FA, for B, you have FB, and so on. And now what you do is you apply the same function across all the ciphertexts. So you apply FA to both LA0 and LA1 across all the ciphertexts. You apply FB to both LB0 and LB1 across all ciphertexts. And you do that for every gate with that wire going in or out. So when you're applying it to the key space of the ciphertext, you use key homomorphism. When you apply it to the message space, you use the message homomorphism. Now, that's how you re-randomize a garbled circuit. Now, re-randomizing a garbled circuit is all good, but what you also need is to change the message labels, the input labels to match, right? So for the we have the first server, it garbles a circuit and it creates the input labels. Now it it samples a key for each input label and it encrypts the labels with it. And recall in the two-party protocol, there was an OT with the input labels, right? Now what we use in the OT is these keys instead. And the encrypted labels are posted. Now, when you re-randomize, what happens is you can easily apply the same function. The re-randomizer can see the ciphertext. It can apply the same function to the message space. So whatever it applied to the circuit to re-randomize, it applies to the message space in the encrypted label set. And then it also applies one transformation each, a different transformation to both the keys. And it uses these for OT. So that's basically how you do re-randomizable garbling. So we are finally ready to see what a scales protocol looks like. And so the scales protocol uses a re-randomizable garbling scheme. It uses a 2-round Oblivious transfer. We've seen both of these before. And it uses key and message homomorphic encryption, which we briefly saw when we were creating a re-randomizable garbling. So here is how it's done. So the first message, the clients, recall OT was the two message protocol, and the clients and the receiver sends the first message. So the client, as the receiver, uses its input bit as a choice bit and puts the first message on the bulletin board. And that's it. Then the first server comes up, it garbles the circuit, it creates, and for each label, it samples a key, it encrypts the label with the key and creates an encrypted label set. And then it creates an OT second message, the sender's message, with both these keys. Now it posts the garble circuit, all the encrypted labels, and all the OT second messages onto the bulletin. The next server comes up, it reads the garble circuit and re-randomizes it. It for the encrypted label set, it applies the offset function to the message space so that the labels match the new garble circuit, and it samples two functions and applies them to the key space, and then it creates an OT2 message with these two functions that it applied to the key space. And now it posts the re-randomized garbling, the re-randomized encrypted label set, and the OT2 message. Every garbler after that, or every server after that, does exactly the same thing. And then finally, what happens is the clients, they read all the OT2 messages. Yeah, they decode the output of the Oblivious transfer. They create the final key by applying the functions that each re-randomizer applied to the initial key. Then it decrypts the final encrypted label to get the last label. And that is what it posts as its final output. So now on the bulletin board, we have all the labels corresponding to the final garble circuit. We have the final garble circuit itself because the last server posted it. And anybody can come up and read this and evaluate f of x. And that's the scales protocol. So, and I'm just going to be concluding with a short performance comparison. So we're talking about scales and YOSO because they're the most relevant over here. And So the setup that Scales requires is a bulletin board. YOSO requires target anonymous channels and a PKI. So Scales does not require that. And in particular, to get target anonymous channels, you need honest majority, and you don't need that in Scales. And yeah, so where communication pattern is concerned in Scales, we relax it by saying the clients can speak twice, once at the beginning and once at the end, and each server participating in the computation speaks once. And whereas in YOSO, this distinction does not exist. Everybody speaks once and erases their state. And yeah, so the number of rounds of communication in YOSO is, in Scales is constant, but in YOSO is proportional to the size of the computation. So for us in Scales, no matter how big F is, you can get away with just say 2 or 5 or something rounds of
Anasuya, can you hear us?
participating servers.
Anasuya, we lost after you talked about communication. You could repeat a little bit.
Hello?
Yeah, can you hear me?
Yes.
You could
So
when you start talking about corruption.
okay. So in the corruption model, Scales, for now, we support semi-honest adversaries and adaptive corruption. And in YOSO, whereas YOSO supports malicious adversaries, we allow all but one corruption of the servers, where YOSO requires that each committee has an honest majority. And among the clients, Scale supports an arbitrary number of corrupt clients, so does YOSO. And yeah, the number of servers itself that participate in the communication is a constant as compared to the entire server space. And in YOSO, the number of servers that participate grows proportionally to the size of the computation, because that many rounds are required and each round has new servers. So that's basically it. Thank you.
Okay, thanks, Anasuya. Any quick questions? I know we are cutting off a bit, so something was not clear. But unfortunately, we won't be able to.
So we can find more detail.
URL. It's also appearing at TCC. The no questions. We'll just so Mukul, you could stop recording.
Thank you.